welcome to the next lecture. So, in this lecture we will be seeing the choice of benchmark. So, in the previous lecture what we have said is that how do we compute the execution time of a program. So, and then we know that these are the ways through which you can compute the execution time of a program. Now, still how you can say that this computer is better than this? Choice of benchmark, that means what you will be using, which benchmarks to use, such that you can say that okay, by executing this set of instruction I can say that my computer is giving so and so performance. So, basically here the basic concept is how to compare the performances of two or more computers. This is what we are discussing from the last lecture as well. So, we need to execute some programs and measure the execution times. Set of standard programs are used for this comparison, and we call this as benchmarks. So, benchmarks are nothing but some set of programs which are set as benchmarks basically for this comparison. And various metrics have been proposed to carry out the evaluation. We will be discussing that next. So, let us see some early metrics that are used. One is millions instructions per second. This is computed as instruction count divided by execution time into 10 to the power minus 6. So, this is dependent on what? So, basically we are trying to get how many millions of instructions that are executed per second. This is dependent on instruction set, which makes it difficult to compare MIPS of various computers with different instruction set, because see, different computers will have different instruction set, different kind of architectures, but then how we can say that this can be a metric that can be used to evaluate for all. So, this becomes difficult. So, as this is dependent on the instruction set, because the instruction set cannot be same for two computers. MIPS also varies between programs running on the same processor. Why does this varies? Because different compilers will generate different codes. Suppose say you have ran a particular program and it has generated some set of codes. The same program can be run and the compiler may generate little different code. So, at that point of the time also this MIPS will be different, and also it has been observed that higher MIPS rating may not mean better performance. So, we cannot say that if the rating, that is the MIPS rating is high, that means it performs much better. Let us take an example, a machine with optional floating point coprocessor. So, when a coprocessor, so the meaning is that we have a machine with an optional floating point coprocessor. So, when coprocessor is used, overall execution time will be less, because you are using a coprocessor in which the task can be performed in a much faster fashion. So, in turn your execution time will become less, but for doing so you may use some complex instructions. So, if you use complex instructions, then it will give you a smaller MIPS value. So, when you use a coprocessor, your overall execution time becomes less, but you are using more complex instruction for execution. That is, the MIPS will be much less. Same way for a software routine, it takes more time, but it is giving higher MIPS value. Why? Because there will be more number of instructions that are getting executed, but in turn the time using a software routine will be much more. So, this is a fallacy. This is a problem here. So, we are using a coprocessor which is making the entire process faster, but still we are getting smaller MIPS. But another which is using a software routine which is getting higher MIPS, but at the same time it takes more time as well. So, MIPS rating is only valid to compare. So, MIPS rating is not valid to compare everywhere, it is only valid to compare the performance of two or more processors provided that the following conditions are satisfied. If the following conditions are satisfied, then only we can say that MIPS rating is valid to use. What are the factors? First one is the same program is used, the same instruction set architecture is used, the set of instructions should be same, and the same compiler is used. If you have all these things together in place, then only we can say that MIPS rating can be taken for performance comparison. So, in other words, we can say that the resulting programs used to obtain the MIPS rating are identical at the machine code level with the same instruction count. You must have same instruction count, you must have same those machine code level instructions. Then only you can say that you can use MIPS as a metric to evaluate the performance. This is million floating point operations per second, MFLOPS. So, it simply computes the number of floating point operations executed per second. Now, this obviously will be more suitable for certain applications where we will be using floating point computation. Let us say for certain application there are not so much floating point instructions. So, in that floating MFLOP will be much less, but that does not mean that the performance of that is poor. So, here again different machines implement different floating point operations, and more suitable, and as where it is more suitable for applications that involve lot of floating point computations. So, different floating point operation takes different times. Addition of a floating point will take less time maybe compared to the division of a floating point. So, we cannot really say that how that MFLOPS will give you a MFLOPS is a metric which will give you a correct performance evaluation. Compilers have no floating point operation and have MFLOP rating as 0. There can be some compilers that do not have a floating point operation, and for that this MFLOP will be 0. So, the rating will be 0 for MFLOP. Hence, this is not very suitable metric across machine and across programs. MFLOPS cannot be used as a metric across any machines or across any programs, because different machines have different features, different characteristics. So, it might not be a good idea to rely upon the metric like MFLOP. Let us take an example. Consider a processor with 3 instruction classes A, B and C with the corresponding CPI values being 1, 2 and 3 respectively. The processor runs at a clock rate of 1 gigahertz. So, for a given program written in C, 2 compilers produce the following executed instruction counts. So, instruction count for A type instruction is 7 for compiler 1, 2 for instruction type B type instruction and 1 for C type C classes. Similarly, for compiler 2, the number of instruction count for A type is 12, B type is 1 and C type is 1. Let us see how do we compute the MIPS rating and the CPU time for the 2 program version. So, we have been given with the CPI values for the various types of instruction, that is A, B and C as 1, 2 and 3 respectively, and the processor runs at a clock rate of 1 gigahertz. So, these are the parameters which are already given. Let us see how we will calculate the MIPS rating and the CPU time. So, MIPS is clock rate in megahertz divided by CPI, and CPI is CPU execution cycle divided by instruction count, and CPU time will be instruction count multiplied by CPI divided by clock rate or multiplied by clock period. Let us say for compiler 1, 7 is the total number of instruction type A, which is multiplied with 1, that is the CPI for that particular type A instruction. Similarly, 2 multiplied by 2. So, basically we are doing 7 multiplied by 1, 2 multiplied by 2 and 3 multiplied by 1 for compiler 1. So, 7 multiplied by 1, 2 multiplied by 2 and 1 multiplied by 3 divided by total number of instruction. Total number of instruction was 7 plus 2 plus 1, that is 10. So, 14 divided by 10, which is coming to 1.40. Similarly, MIPS rating will be 1000 megahertz divided by 1.40, that is 1 gigahertz. The clock rate is 1 gigahertz. So, we converted it to megahertz because we have to find out in terms of MIPS. So, that is 1000 divided by 1.40, that is coming to 714.3. Now, what is the CPU time? The CPU time can be calculated by 7 plus 2 plus 1, total number of instruction, into in millions, because this is given in millions. So, into 10 to the power 6 into 1.4, that is the CPI, multiplied by clock period or divided by the clock rate. So, we get the time as 0.014 seconds. So, this much second it is taking to execute for compiler 1, and the MIPS rating for this is 714.3. Let us take for the next compiler. In a similar fashion, we compute the CPI 12 into 1, 1 into 2 plus 1 into 3 divided by total number of instruction, and we get 1.21 as the CPI. Similarly, MIPS rating can be found out by 1000 megahertz divided by 1.21, that comes down to 826.4 MIPS. And similarly, for CPU time, we will use the same instruction count multiplied by CPI divided by clock rate, which is coming down to 0.017. So, now you see that the MIPS of this is higher. So, it has got higher millions instruction per second, but the execution time of compiler 1 is less. So, here you can clearly see that the execution time of compiler 1 is less, but the MIPS of compiler 2 is more. So, MIPS cannot be the right choice for in such cases. So, MIPS rating indicates that compiler 2 is faster, while in reality the reverse is true. Now, let us take an example. So, this is a C loop. What we are doing inside this C loop, for k equals to 0, k less than 1000, k plus plus, we are simply adding a constant value stored in variable s to ak, that is first array element, and we are storing back in ak. Similarly, for the next one, and this is going on in a loop. Let us write the assembly language code for this particular C code segment. So, these are the few things you have to consider. T1 stores the address of s. S is a variable which is a constant, some value is stored here, and T3 stores the value of s, and T2 points to the first location of this array, of this particular array. So, here initially what we are doing, we are loading the word from this location 0 of $T1. $T1 is having the address of s. So, value of s is stored in T3. We are adding an immediate value to T2. What T2 contains? T2 contains the points to the first array, that is first location of the array, and we have to compute something for this. How many times? 1000 times. So, we are multiplying 4000, we are adding 4000 to T2, because each are 4 by. So, 4 multiplied by 1000. So, which is coming down to, we are adding it to T2 and we are storing it in T6. So, T6 stores the final value. So, we have to go till that value to execute it. Next word, inside the loop, these are the following statements that are getting executed. First, what we are doing? We are loading the word from the first location of the array, that is A of 0. We are storing it in T4. Then what we are doing? The value of S is stored in T3 and the array value is stored in T4. So, T3 and T4 we have to add and we are storing it in T5. So, finally, we are adding T4 and T3 and we are storing it in T5, and finally, we are storing back this T5, the added value, in 0 of T2. So, in that location we are again storing it back. And finally, what we have to do? We need to increment to the next location. So, the first part is done. Now, we are moving to the next location. So, for the next location, it is added with 4 again and then it is transferred there. Now, branch if not equal we are doing such that whether we have reached to that point or not. T6 is equal to that T2, because at every point we are adding 4 to it. So, when it reaches the last element, it will come out of the loop. When till it is not equal, T6 is not equal to T2 is not equal to T6, we will loop. When it is equal, it will come out of the loop. So, these are the following assembly language code that we are executing for this set of codes. The code is executed on a processor that runs at 1 gigahertz, that is the clock period is 1 nanosecond. There are 4 instruction types with CPI values as shown in this table. Now, see ALU operation. Which are ALU operation? Add immediate, add immediate. These are ALU operation, and the CPI of those operation is 2. Similarly, you have load. Load is load word, load word. The CPI is 5. You have store word. The CPI is 6, and you have a branch in type of instruction where the CPI is 3. So, these are the CPIs of various kinds of instruction, and this is the program code which contains all these kinds of instruction type. Like ALU, these are the ALU type instruction, load word is load type, store word is store type, and branch if not equal is a branch type instruction. Now, let us see. The code has 2 instruction before the loop and 5 instruction in the body of the loop that executes 1000 times. Is it true? So, outside the body of the loop you see you have 2 instructions, and inside you have 5 instruction 1, 2, 3, 4, 5, and each of these instruction is executed 1000 times, because this loop is executing 1000 times. So, what will be the total instruction count? There are 5 instructions and each instruction executes 1000 times. So, 5000, and 2 instruction outside the loop plus 2, it will become 5002. Number of instructions executed and fraction Fi for each instruction type. So, let us calculate this. Number of instruction executed and fraction of instruction Fi for each instruction type. Let us first calculate the total number of instructions. So, outside the loop there is 1 ALU instruction and inside the loop there are 2 ALU instructions. So, these 2 ALU instruction each will be executed 1000 times, and this instruction will get executed 1 time. So, inside the loop there are 2 ALU instruction which is executed 1000 times, and this is executed one more time. So, 2001. Similarly, you can calculate for all load, store and branch. Store and branch are only one instructions are there. This is store and this is branch. This is executed 1000 times, this is executed 1000 times. So, what is the frequency? Total number of instruction of such kind divided by the total instruction that are there, which is coming to 0.4, that is 40%. This is coming 20%, this is coming 20% and this is coming 20%. Now, how do we calculate? This is the frequency of ALU kinds of operation. This is the frequency of load type and so on. So, total CPU clock cycles is 2001 multiplied by 2, 1001 multiplied by 5, 1000 multiplied by 6, 1000 multiplied by 3. So, we are taking all this from this CPI. We are multiplying this CPI with the total number of instruction that we have found out previously, and we are getting the total cycles as this much 18007. What will be the average CPI then? This is the CPU clock cycles divided by instruction count. So, this is the total CPU clock cycle divided by instruction count. You get the CPU as 3.6. Now, you can calculate the total execution time, which is IC, which is total instruction, which is 5002, CPI that we have calculated, and this is the clock period, which is coming to 18 microsecond. This is how we calculate it. Now, how do you see the clock rating? Clock rating will be clock rate divided by CPU, which is coming to 277.8 MIPS. So, the processor achieved its peak MIPS rating when executing a program that only has instructions of type with lower CPI, that is ALU type instructions. So, if you only execute such kind of instruction where the CPI is less, that is you see the CPI of ALU type is only 2, but for store, load, branch is more. Now, if you only execute that is ALU, which only those type of instruction where CPI is less, then you can get the peak MIPS rating, that is coming to 500 MIPS. But if you use with this mixture where the CPI is found out by calculating, taking into consideration all the types of instruction and the frequency at which all these instructions are occurring, then it will be coming to something lesser MIPS. So, next let us see choosing programs for benchmarking. Now, how do we choose programs for this benchmarking? Suppose we are trying to buy a new computer and there are several alternatives possible. So, how to decide upon which one is the best? The best way that can be used is to run the actual application that you are expected to run, that is the actual target workload. That means that particular computer you will be using more floating point operation. So, you should have such kind of program in place which you will run on that machine and you will see that what is the performance coming. So, actually you are running certain applications that will give you the best result. So, choosing the programs for benchmarking is really very important, but not possible for everyone to do this while purchasing. So, what we do, we often rely on the methods that are standardized to give us a good measure of performance. So, there are some standardized methods that are used which can be considered as a good measure for this performance. So, different levels of programs are used for benchmarking. One is real application, can be kernel benchmarks, some toy benchmarks and some synthetic benchmarks. Let us see an overview of all these things. What are real applications? Here what happens, we select a specific mix of suite of programs that are typical of large application or workload. Some of the examples are SPEC 95, SPEC CPU 2000 and etc. SPEC stands for System Performance Evaluation Corporation, and this is the most popular and industry standard set of CPU benchmarks. So, spec int 95 consists of 8 integer programs. So, these are some of the information now I will be giving you for this spec standard spec that is there. Spec floating point 95 consists of 10 floating point intensive program. Spec CPU 2000 consists of 12 integer programs and 14 floating point intensive programs, and spec CPU 2000 consists of 12 integer programs. So, these are some of the information and 17 floating point intensive programs. So, as we are moving from 95 to 2000 to 2006, the numbers are increasing. So, we are putting more workload because the advancement in these clock speed is increasing. So, we can actually perform more operations. So, that is how it is moving. So, these are spec 95 programs integer. What all kind of programs that are present? A game based on artificial intelligence, a simulator for Motorola 88K chip, a GNU compiler, a compression and decompression utility, Lisp interpreter, image compression and decompression utility, Perl interpreter, a database program. So, this spec 95 program consists of these following benchmarks. Similarly, spec 95 programs consist of these programs, and these are all these spec 95 programs of floating point programs. So, they have a mesh generation program, shallow water modeling, quantum physics Monte Carlo simulation, solving hydrodynamic Navier-Stokes equation, multi-grid solver on 3D potential field, and so on, quantum chemistry simulation and so on. So, these spec 95 programs were having these programs. Similarly, CINT 2000, that is integer, consists of these following programs. So, these are the 12 programs apart from. So, they added something new, which is VLSI place and route. So, these were also added in this group theory interpreter were also added, which was not there previously in spec 95. So, these are some of the programs of CFP 2000. So, it has got quantum dynamics, these are already there, neural networks were added, pollutant distribution is added, nuclear accelerator is added, and many more. Now, let us see what is kernel benchmark. Here, what happens basically, key computationally intensive pieces of code are extracted from real programs. So, let us say there are part of the program where the computation requirement is more. So, they take out those part of the program from there, and what they do, unlike real programs, no user would be running the kernel benchmarks. They are solely used to evaluate performance. So, basically there are some part of the program, real program, where the operations which you are performing is much more. So, we take out those portions, and what we do, I mean, unlike real programs, the user will not be running the kernel benchmarks definitely. They are used solely to evaluate the performance. This is just used to evaluate the performance. And as we know that kernels are also best to isolate performance of specific features of a machine and evaluate them. Some of the examples are Livermore, loops, linpack, etc. And some compilers were reported to have been using benchmark specific optimization so as to give the machine a good rating. That means, let us say we have so many benchmarks now. So, now these are already available and you can use this to evaluate your performance. So, some compilers typically use some of those features to accelerate the speed of those programs only, but it may not work for any application. It may work for specifically for those applications, but if you are not using such kind of constructs that are used in those programs, then you will not be getting better result. These are some toy benchmarks are also used. They are small pieces of code, typically between 10 to 100 lines, and they are convenient and can be run easily on any computer. They have limited utility in benchmarking and hence sparingly used. Some of these are some of the examples. Now, coming to synthetic benchmarks. What do you mean by synthetic? By synthetic, what we mean is that those are generated. So, we know that this particular machine has this much type of ALU operation, this much type of store and load operation. So, some synthetic benchmarks are generated which will actually resemble to that particular frequency of operation which is performed for certain programs, but they are synthetic, they are not real benchmarks basically. So, somewhat similar to the principle to kernel benchmarking, but they try to match the average frequency of operations and operands of a large program. Just now what I have said, let us say we have a program and we know that for this program 80% will be such kind of instruction ALU operation and 20% will be store load operation. So, we also generate a particular program such that it uses same kind of features, 80% will be ALU and 20% will be other. Synthetic benchmarks are further removed from reality than kernels, as kernel code is extracted from real programs, while synthetic code is created artificially to match an average execution profile. So, these are made artificially to match a average execution profile. Some of the examples are Wheatstone and Drystone. These are not real programs. So, these are synthetic programs. So, we came to end of lecture 13. So, where we have seen that what the choice of the benchmark, how do you choose a particular benchmark. So, that entirely depends on the application for which you are designing or you require the CPU for what kind of application. Thank you.